Hello, my name is Sharon, and today I wanted to tell you a little bit about one of my favorite theorems in calculus, which is the Riemann rearrangement theorem. All right, so before we get to the theorem, I have to introduce a couple definitions that the theorem is related to and that are related to series. All right, so we say that a series is absolutely convergent if the series that results when you take the absolute value of every term is convergent. And we say that a series is conditionally convergent if the series converges, but if the series that results when you take the absolute value of every term diverges. So as an example of a conditionally convergent series, a kind of classical example of this is the alternating harmonic series. So if we take kind of the absolute value of the terms of the series, we just end up with the series 1 over n, which is the harmonic series and which we know diverges. On the other hand, if we look at this alternating harmonic series and test for convergence, which we can do using the alternating series test, we'll see that it actually converges. So if we look at the limit as n goes to infinity of the non-alternating part, we'll see that that limit does indeed equal 0. And we also know that as n is increasing, 1 over n decreases, and so that sequence is decreasing. And therefore, the alternating harmonic series converges. And this is illustrated in these plots below. On the left-hand side, we have the sequence of partial sums for the absolute value sequence, and which is kind of just the regular harmonic series. And we can see that there's this growth here, and we don't have convergence, whereas on the right-hand side, where we have the sequence of partial sums for the alternating harmonic series, we do get convergence. So because we have the series converging, but the absolute value of the terms of the sequence and that series diverges, we say that this series is conditionally convergent. All right, so now we can move on to the next question, which is, what happens when you rearrange the terms of a series? So we know that 1 plus 2 plus 3 is 6. And we also know kind of trivially that if we rearrange these numbers, we will always get 6, no matter in what order we take this sum in. So a relevant question might be then, is this also true for infinite series? And it turns out that it depends. Moreover, it actually depends on these definitions which we just introduced about absolute and conditional convergence. So part of one of these results related to this question is that any rearrangement of an absolutely convergent series will have the same sum. So just like in this finite case up here, if we rearrange the terms of an absolutely convergent series, we will always get the series to diverge to the same sum. However, this isn't quite true for conditionally convergent series. So we have a theorem known as Riemann's rearrangement theorem, and Riemann's rearrangement theorem tells us that if we have a conditionally convergent series of real terms and we have a given real number, then there exists another sequence, which is another series, which is a rearrangement of an, and this rearrangement converges to the real number. So I was completely blown away when I first heard of this theorem, because to me it was pretty crazy that you can have this series of numbers, and yeah, maybe it's infinite, but it still seems crazy that you can rearrange them to equal anything that you want. And so for me, that moment of learning that was kind of representative of one of the reasons that I really enjoy math, which is that math is always full of surprises. You might learn about something in a class, and you might learn about it in a very specific case of it, and maybe not even realize that it's a specific case of it. And then later on, a couple of years down the road or a couple of classes later, you might learn about how to generalize what you learned to a higher dimensional case or maybe an infinite case of something. And you might realize that things that you took for granted, you can't take for granted anymore. And the questions that you may not have even asked are suddenly really hard questions or really deep questions in these higher dimensional or infinite cases. And oftentimes that results in surprise. And it's one of the things that I really enjoy about math and one of the reasons why I want to continue studying math. Hopefully this was interesting, and I thank you for your time.